Well, organic materials. Here we are. Oh, so the stage is yours.
Okay, thank you very much, Will, for that introduction. Earlier on, I think you described myself and Radovan as holograms. I think actually I feel more like the pantomime horse, because I actually started off the first talk of the powder-specific session, and now I'm closing it. So what I'm going to be talking about here is organic materials, and I struggled, as Radovan did, with inorganics to think what exactly can one say about a subject that's as broad as organic materials. So again, it's a bit of a curate's egg of topics, but hopefully ones that you'll find interesting. But before we get into the meat of that, just a couple of late additions based on conversations and observations. I spoke to Ian Madsen at lunchtime, and he pointed out that there is an executable still kicking about somewhere in cyberspace for those that want to calculate. In fact, yes, Ian's holding his hand up. Has he found it?
I have indeed found it. I've downloaded it to my computer. Anyone who wants it, come and see me.
Fantastic, thanks, Ian. So anyone who wants to calculate a variable count time scheme, doesn't want to write their own program, Ian has a simple, I believe, DOS-based code and source code for doing that. I noticed that in Peter's indexing example, he showed an example of a very weak peak at very low angle. I really just wanted to highlight that because earlier on in my presentation, I talked about the importance of getting the background down at low angle and eliminating as much scattering, and I thought that was a very good illustration of a peak that could easily be lost. And then Joel Bernstein made a comment that also data provenance obviously is important, but also access to data and its longevity is important. So if someone has collected a data set, is it still going to be available in 10 years' time? And that's something that I'm actually going to speak about on the last day in the future of computing. So fortunately, after Radovan's introduction, I had actually put in a definition, and I took the coward's way out and used someone else's definition so I can deflect responsibility if you disagree with that. So I took my working definition from the Cambridge Structural Database, and I won't bother reading it out. But simply put, most organics contain the materials, the elements that are shown at the bottom of the slide here. Typical organic powder X-ray diffraction pattern, there are certain things that are almost universal when you collect your pattern. The first thing is this fall off in intensity with angle, increasing angle that we mentioned earlier on, which is a function of the Lorentz polarization correction and also the form factor fall off. The other thing that's notable is the increasing reflection density, as several of the speakers have pointed out. As we move from low angle up to high angle, these tick marks representing reflection positions get more and more dense, and you can see the overlap that Lynn spoke of, which gets particularly severe at high angle. So I took typical, in quotes, organic unit cell, P21 over C, with a volume quite large actually, of about 3,000 cubic angstroms. And if you look at the average peak density over the low angle region for this material here, it's less than 2 peaks per degree. Move a little bit up to the mid-range, the average density has moved up to about 7 per degree. And by the time you hit the end region, we're looking here from about 50 out to 65 degrees. This is on, I should emphasize, on a lab data set collected at 1.5. So this is a roughly 1.5 angstrom resolution. We'll see that we're up to a peak density of 35 reflections per degree. Now, you'd be lucky if you could identify 35 intensities, full stop, in that region. So that gives you some idea of the amount of bunching up that you have seen, again of the type that Lynn illustrated very clearly earlier on. And so this is a fundamental problem for organics, particularly because it's this high angle area that's going to pin down the fine detail of the structure and tell us that our structure is being fitted properly. As we saw earlier on, it's actually often possible to fit the low resolution part, the low 2 theta end of a pattern quite happily. Peter showed it in indexing, index a subset of reflections, and then things start to move out of register as you move higher up. It's exactly the same with organic materials, relatively easy to solve at low resolution, not so easy to pin down the level of detail at high angle. So why exactly is it so severe? Well, it's really a function of cell size. Organic molecules tend to be, well, they come in all shapes and sizes, but they can be very large. I guess in the limit, they can go up to proteins. So de facto, you have a lot of reflections, and the space group symmetry is relatively low, so the chances of accidental reflection overlap as opposed to systematic are relatively high. So I guess most of you, and certainly those of you who work with organic materials, know that the bulk of organic materials crystallize in a very few space groups. The most popular one being space group P21 over C. And so what I did was I took the latest release of the Cambridge Structural Database and went through and found out roughly how many entries there were as a fraction of the total number of entries in the database, and just of organic entries, I should say, those that are actually marked organic, so we're not counting organometallics. And these are the numbers that come out. And so you'll see that there's a significant number of materials here crystallizing in these 5 space groups, all of which are relatively low symmetry. So they're going to give rise to unit cells that generate patterns with lots of reflections, and those reflections are going to overlap. We really can't get around it. Looking at it as a function of cell size for a very, very simple example, just illustrating the effect of symmetry here, going from triclinic to cubic, the number of independent reflections here, well over 3,000 for a big cell, whereas only 300 for the cubic version. The other thing I mentioned is that we have the problem of the form factor fall-off. With most organic materials, the heaviest atoms that you will find will be chlorine and sulfur. And they're, in the great grand scheme of the periodic table, not got that many electrons. And as you know, the scattering power of an element at 0 sine theta over lambda is the number of electrons. So we're already starting off from a relatively low point here, relative to, say, a metal, such as uranium, where it's kicking off at 92. And then as a function of sine theta over lambda, the scattering power drops really quite rapidly down to low levels. And to make matters even worse, of course, that basic form factor becomes modulated by the temperature factor. So the higher the temperature, the quicker the drop-off will be. So what is the bottom line? Why am I telling you this? Well, it's simply to say that we really do, with molecular organics, struggle in many cases for high-quality diffraction data, particularly at high angles. Yes, we can go to the synchrotron, but as we showed this morning, you're sometimes struggling to avoid radiation damage. Normally you would think that with the extra photons you would get better signal to noise, and that's certainly true, and you can go out to higher angles and pick up weaker signals, and certainly in general the resolution at a synchrotron of the instrument is going to be much higher, so you can circumvent some of the problems associated with overlap. But if your sample fries, you may not be able to easily get enough data to do anything useful with it. Within the laboratory, we have no trouble with sample burning, but despite the advances that we've seen in diffractometers in the lab with detectors, in absolute terms, we struggle for instrumental resolution relative to the synchrotrons. Direct methods, as Lynn was emphasizing earlier, and I put in the caveat conventional, because we'll hear about how direct methods have moved on massively and adapted to the powder problem. If we just take them in their native form as developed for single crystal work, they really do need accurate structure factors collected to atomic resolution. And it should have been obvious from the pattern that I showed earlier that that is not something that we're going to be able to do very easily. So if we get to the if we're lucky enough to solve either using global optimization or start to refine, we need an accurate molecular description one way or another if we're going to successfully wrap up an organic crystal structure. So we've seen some pointers earlier on to what's going to be happening later in the week. The full story on direct methods and global optimization. I think I've said Wednesday, I'm not entirely sure that I've got that right, so check the timetable. But for the moment, I'm not going to discuss global opt at the moment, other than to say that we do need an accurate starting model for global optimization to be successful. Basically, some sort of accurate description of the molecule that we're going to be studying. And I'm going to talk a little bit more about that in the case of the molecular organics. Before we go on to that, and this is all, as you will see, it all links together. If you ask yourself the question, how should I finally refine my structure? There are various ways that you can do that. In Rietveld, you can do it as a free refinement, i.e. just as you would in single crystal, let the atoms go where they want to, driven by the least squares. You could say, well, actually, I don't think I've got good enough data to do that, so I'll allow the least squares to drive it, but I will also apply a set of restraints based on some criteria, generally speaking chemical sense, which will balance the drive to minimize the RWP. Or you could go one notch higher in terms of restraints and say, no, I will actually refine my structure as a series of rigid bodies. The key thing, and we've heard this now several times to do with structure verification, is that the fit to the data is important, but not at the expense of chemical sense. You can't turn around and say, I've got a great RWP if your molecule is badly distorted. So I think in many cases we can acknowledge that a free refinement, i.e. the powder equivalent of a single crystal refinement, is really rather unlikely unless we have exceptionally good data. So if we acknowledge that, then we know that we're going to have some sort of restraint or rigid body to guide our refinement. And so I would argue that there's a lot of sense in, if you're going to be doing global optimization, starting with an accurate description of your molecule, and then carrying that through, because that starting model will permeate through the structure solution geometry as the input geometry that you get, plus whichever torsion angle values are input by the global optimization procedure. And then your rigid body geometry in the refinement will basically be that output by the structure solution. So if your input geometry is good, then the rigid body geometry is good, and the structure refinement becomes relatively easy. Right. Hands up before I offend anyone. Hands up anyone who had anything to do with this material here, IBPRAC 04. Is there anyone in the audience that was involved in solving this? And in case you've forgotten, it was published in Acta B about a year or so ago. Fantastic. Not that I was going to insult you anyway. The people that I'm going to insult are, did anybody referee this paper? Because if I'll see you in the courtyard. If you did, This is the sort of structure that gives powders a bad name. It's formed to ibuprofen. It's in the database, it has been published in Acta B, and it's wrong. Now, interestingly, it's not that wrong. And why do I say that? Well, actually, because I was involved in solving it about 2 years before it was published. But we solved it, we could fit the data reasonably well, but we could not refine it properly. The structure just would not behave. So it's approximately correct. We know that we have a reasonable description of what is going on within the powder, but there's something that we are not modeling correctly, and we haven't been able to get to the bottom of it. So when this was published, we thought, oh no, somebody's beaten us to it. Downloaded the CIF, had a look, and realized, no, they've actually published fundamentally the same thing that we had, but even worse than that, they'd gone on and refined it, and this is the output. Now, just to point out what this is, here's a carboxyl at the end. That does not look like any carboxyl I've ever seen or you will find in the database. This is a benzene ring here, so one might expect that that CC bond would come off in the plane of the benzene ring. So this structure is wrong, and you can tell it's wrong by performing a quick check on it. Now, quite why the CIF checker didn't pick up this geometry, I don't know. But I dragged and dropped it onto Mogul, which I'll talk about a little bit later, and you can see that Mogul flags up things as unusual, 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 unusual. That's not a good sign. There's no advantage saying, oh, let me show you this unusual structure. Let me show you this structure that is wrong. And the worst part of it, and I've saved this for last, is that it's not even a great fit to the data. If it was a perfect fit, I could understand it, but it's not. So, quite why this got through, I don't understand. It's clearly not right. It is a metastable form. It's produced by cooling a molten version of ibuprofen and then allowing it to kneel for about 8 or 10 hours. The authors actually say that the metastability is probably why it doesn't fit the data, but that's not an excuse. Metastable crystal structure is still a crystal structure. You ought to be able to define it correctly. So that's an example of the sort of thing that we're trying to avoid. So when we start to ask questions about where can we get good starting structures from, then there are various ways or various places that we can look. So imagine that you have a second form of some known material, a new polymorph. Then as your starting model, it would be eminently sensible to use the molecular structure that's already been determined for the known polymorph. If it's some modification of an existing molecule, then you should probably use that existing structure taken from the CSD, but modified in some way, maybe through modeling software or even manual manipulation of files. If it's a completely new structure, you can quite easily pull together known fragments from the CSD and stitch them together to create that. Or you can start from scratch with some molecular sketching, followed by the use of optimizers. And if your molecule that you're looking at has some various fused ring systems that you're not exactly sure of their conformations, then you can use other programs such as Carina to come up with likely starting conformations. So there's plenty of prior information out there. If you want to validate or somehow check your structure, maybe one that you've sketched in a sketching molecular program, then generally speaking, a basic quick structure, tidy up, clean, maybe a molecular mechanics, generally isn't good enough to carry that structure forward. Something of a Gaussian type optimization is going to give you a molecular structure with higher accuracy, bond lengths and angles, but of course it won't give you the conformation. That's something that we'll find out in the global opt. DFT will do that to even higher precision, but as we've heard, not always necessarily the easiest thing to use. And there are various programs around to do conformational searches that may give you clues as to how the molecule might fold. When I'm talking about a structural model, as we'll see in many of the demos for the real space structure solution, we're talking about a three-dimensional model. And typically things are parameterized in terms of bond lengths, bond angles, and twists, bond torsion angles, as indicated here. And so when you're constructing the molecule, you could ask the question, okay, I've built my molecule, but what do I have to vary? How accurately do I actually know that molecule? And the answer to that is quite straightforward. It's very intuitive. You would expect that two atoms that are sitting bonded together will sit at the bottom of a potential well, and it will take quite a lot of energy to distort them from their equilibrium position. And within the crystal structures, you could do a search, for example, the bond length between this carbon here and this carbon here, and you find a very sharp distribution with a mean of 1.51 plus or minus a very small standard deviation. So what that's telling you is that within observed crystal structures for that particular motif, you could probably set your CC bond length to 1.51 and not allow it to vary. There's no reason in particular to allow it to vary, at least not during structure solution stage. The same is very much true of bond angles as well, but of course bond angles are slightly softer in terms of the energy that it takes to move them from their equilibrium position that they would be if they were just sitting in a vacuum. It's worth bearing in mind that what we're talking about here is the effect of crystal packing forces on these molecular conformations and bond lengths and angles. But to first approximation, if we have a bond angle, we can treat it as a fixed entity. When it comes to torsion angles, it's a completely different story. This is again a search done in the CSD that is showing distribution of torsion angles in the form of a polar plot for the torsion that is this carbon to carbon to carbon to carbon. And it's showing you that virtually any torsion angle, any rotation around that central bond is accessible, but there are three favored areas, which when you look at the structure makes sort of intuitive sense. But these basically torsional parameters are much softer than the other ones, and they are something that we cannot in general fix in advance. So I must have been reading too much Shakespeare. I think I did a to fix or not to fix. So this is now the question, as opposed to grinding. In general, we can fix lengths and angles in a structure solution and just allow the torsions to vary. We can consider allowing lengths or angles to vary in the refinement if we think that there is any uncertainty over the starting value, or that our searches have shown that there's quite a wide distribution, or that the fit to the data isn't satisfactory with the model that we're using. We may allow these bond lengths to vary, ideally subject to some limitations. And several people have shown that it can be advantageous to allow bond lengths and angles to vary during structure solution as well. It sometimes helps the speed of convergence of the structure determination. So it's not an absolute thing. I tend to keep these things fixed during structure determination stage, but there are other more flexible approaches can be used. I would say one of the most useful tools that I've come across in recent years is a program called Mogul, which is actually distributed along with the Cambridge Structural Database. And it really is a fantastic piece of software, both in terms of creation of models and actually also verification of models. So I won't go into it in detail. I've got it on the laptop if anyone's interested in seeing it in action. But basically what you can do with Mogul is drag and drop a CIF file on, either highlight certain bond lengths or angles that you wish to have check, or just allow it to check the whole molecule. And what Mogul does is analyze the bonds within the molecule, and then go off and query, in effect, the Cambridge Structural Database to find different representatives of each of the bond types within the database. And then it will report back as to whether your molecule fits within the expectation values derived from the database or whether it deviates in some significant degree. And that can be incredibly powerful in setting up a structural model that you know is consistent with prior knowledge. And of course, with anything, you always have to be careful that you aren't, in fact, constraining yourself purely by prior knowledge, but it's certainly a very useful guide. Here's an example of the output here, where you can see that this has been toggled for just the bond lengths at the moment. It will tell you the number of times a bond has been found, where its minimum, maximum, and mean is, and what the observation is within the structure. And then it will calculate this thing called the Z-score. The higher that is, the more it has deviated from the distribution. The lower it is, the more consistent it is with observation. So a very useful tool in structure verification. I think it must be psychic, because Peter mentioned in his talk indexing and the importance of volume. He skipped, I think, one step in several of the examples. He went straight from the lattice parameters to checking them out in a poly refinement. What I tend to do with molecular organics, particularly with stuff done in the lab, where the indexing figures of merit maybe not as high as you would get from the synchrotron, and you have multiple possible candidate solutions, is the first thing that I do is look at the molecular volume and ask, does that volume make sense? So your indexing gives you a unit cell, which is a certain volume. You can estimate the volume of the molecule, and so that divided by that should give you a crystallographically sensible value. So if you do that sum, and for example, in a monoclinic cell it turns out to be 4, plus or minus a very small amount, you can generally proceed and go on and do your poly refinement to verify that. If on the other hand it turns out to be 2.3, you might hesitate before wasting your time setting up a poly. But in terms of estimation of molecular volume, Peter used, he said, an average value of about 17. I think most single crystallographers would stick to what's called the 18 angstrom rule, where you just take all the non-hydrogen molecules in your organic and multiply it by 18 cubic angstroms, and that gives you the volume of the molecule. Now that, even I can work out that sum, even late night on a beamline, so that's the way that everybody does it. But in fact, there's really a much more accurate way of doing it that was published by Hofmann several years ago. It's basically a refinement of the 18 angstrom rule. The 18 angstrom rule is derived from the structural databases. Hofmann's approach is equally derived from structural databases, but on an element-specific basis. So what he's saying is that for any given element, for example, carbon, it has a molecular volume associated with it, some figure. And so whatever that figure is, multiply it by the number of carbons that you have in your atom, and then do the same for the hydrogens with a different value, and the same for nitrogens, etc. So you just do this little sum over, and that gives you an estimated Vmol. And so what I did, actually I got a student for a fourth year project to do some calculations with 100 organic materials from the database, and got them to calculate the molecular volume based on the 18 angstrom rule and plot it against what we've called V actual, the actual volume from the Cambridge Structural Database. And as expected, you get a straight line, but there's a fair amount of scatter in that. And in some of the cases, that can lead to sufficient deviation from a crystallographically sensible division that it casts doubt on whether you've got the right cell or not. In contrast, when you do it with the Hofmann method, it's a much tighter distribution. It's not perfect, there are still outliers, which we need to still have a bit of a look at. But I think the bottom line is that we should really be moving away from the 18 angstrom rule and Hofmann's, particularly within powder diffraction, because we want to remove any uncertainty that we have before investing time in a candidate solution. When we describe a molecule in 3 dimensions, I think what most programs tend to use is something called internal coordinates. Now, I don't particularly want to go through these, but if anyone's interested in talking about internal coordinates, I can wax lyrical on another occasion. Basically what they are is one way of describing molecules as a set of positions where you place one atom at a reference position and place other atoms relative to that to build up a pattern. Now, in general, you don't need to worry about that in most global optimization programs. That's something you don't need to worry about. But if you find that you want to incorporate some additional information into your structure determination, it can be very helpful to know how to adjust these internal coordinates. And here's some examples of where it might be useful if you're using torsion angle distributions of the sort that I showed earlier on to apply some sort of constraint to an individual torsion. You might use some intermolecular distances or incorporate, as Lynn had mentioned earlier on, information from other techniques. So here's a few quick examples of that. Here's an extreme example of a torsion angle that the automatic input of a global optimizer may not pick up on, and this is an amide bond. It might just pick that up and identify it as a single bond and say that you would rotate it, whereas any self-respecting chemist would recognize that the chances are that's going to be trans at 180 degrees, and that's what the database tells you. So you can actually go in and modify the internal coordinates that have been created by the program and fix it at the highly likely value of 180. If you have something like a salt form, you can apply some additional constraints. Here's a very simple example where you search the database looking for this motif here, an interaction between a positively charged nitrogen and a chlorine as separate entities. When you do the search, you'll find an awful lot of observations and a pretty good idea of the distance from the nitrogen to the chlorine and the direction that it's going to take. So instead of treating these as 2 separate fragments, you can actually treat them as one. In order to do that, you need to probably go in and tweak the internal coordinates. In this particular case, the benefit isn't instantly obvious because you're trading an XYZ position for the chlorine atom for 3 parameters here, which are a length, an angle, and I could call it a virtual torsion angle. So we've traded 3 for 3. Where's the benefit? Well, the benefit is that the length to first approximation can be fixed or put a very tight constraint on. The same is true of the angle, leaving only the torsion as variable. So we've effectively taken 2 parameters out of our problem equation. It's also possible to get information from other techniques. This is an example of a cimetidine, probably the second most studied material after carbamazepine in terms of powder diffraction, where a colleague of ours, David Middleton, had collected some solid-state NMR on a specially labelled version of cimetidine and worked out some intermolecular distances. Through what limited understanding of solid-state NMR I have was not a straightforward process. It involved some really complicated pulse sequences and some quite advanced analysis, but nevertheless, he got some useful distances back that allow us basically to pin the molecule down in a set conformation. And the benefit of that in terms of structure determination, these graphs won't really become clear until we've talked about global optimization. But if you imagine this as success rate against time, if we allow cimetidine to solve with all the torsion angles rotating freely, you see that it takes time to build up success. If, on the other hand, you supply a model where you've applied constraints from the NMR, then we get success in a very, very short space of time. So basically we're shifting the information balance from deficit to surplus. Okay, I think we're very much on time. As to whether, is it worth the effort? No, not in this case, because we can solve it completely free. But as an illustration of what may become possible once solid-state NMR techniques become more routinely accessible, I think it's an interesting pointer. I think it's probably a technique whose time has yet to come. Okay, so Lubo has given me the 5-minute warning, and that's good because I'm just on my wind down and I'm about to go into philosophical mode and say, what's the scope of powder diffraction with molecular organics? And being a selfish sort of person, I thought I would pick one of my own structures, one that we did with Bill several years ago now, but just to illustrate what exactly can be done. This is the gamma form of carbamazepine in space group P bar 1 with a Z prime of 4 in it. And you can see that the contents of the asymmetric unit are fairly hefty. But that one is very easily solved by global optimization. Actually, ironically, not by Bill and I, but one of the students at Strathclyde, Philippe, who solved it by doing nothing more than reading in a description of a single molecule of carbamazepine, telling Dash that there were 4 of them, pushing the button, and coming back an hour or so later. Bill and I couldn't go over the fact that it was Z prime of 4. We thought it would probably be too difficult. So it just goes to show what you can do sometimes by just having the courage to tackle a thing without fear of failure. So where does gamma carb in terms of complexity figure in the great grand scheme of things? Well, here's the distribution of a number of entries of molecular organic structures in the latest, or in the November release of the CSD. Here, this is number of atoms, including hydrogen, in the structure versus number of entries. And so this is a sweeping generalization, but if powder diffraction can tackle something complicated like gamma carb, and I could have picked many other examples from many other groups that would show very similar things, it means that we're in a good place. There's a lot of structures that we can potentially tackle, and we shouldn't be afraid to bring powder diffraction to bear on them. Yes, so wrapping up. So yeah, ideally we should be collecting data at the synchrotron, taking advantage of the flux and the resolution, but before radiation damage kicks in. That can only be a good thing. By increasing the use of prior information, we should, and as we'll hear later in the week, be able to do much more complicated structures such as proteins. We need smoother transitions from data to structure. The tools are there. They maybe haven't been quite as stitched together as they should be, but there's an awful lot of them, and it can be done. And we need better integration of methods. And at the risk of boring, I shall raise the V word again, validation. It's very important. From personal experience, we've found that a knowledge, a good understanding of the chemistry of a molecule, coupled with a good fit to the data, is sufficient. But the verification that you get from increasingly accessible methods is certainly can do no harm. Very last slide. If you're going to publish your organic material and you want to avoid going down the ibuprofen form 2 route, check your structure using tools such as this. If they throw up errors, then your structure is wrong and you should look at it. Sorry, that should say in Cypher, using Cypher to check your CIF and deposit your data, as was emphasized earlier on, not just a little picture of it. Put the fit to the data in. And if you need examples, there are plenty of CIFs on the web to download for precedent. Thank you very much for your attention.
Well, alive? Fine? If I were your students, I would love you.
Oh, you love me anyway.
Yeah, definitely, but, you know, later. Okay. So, time for some questions. be patient. Okay. Yes, second. We have got 10 minutes probably. Or can we go on, Bill, a little bit more on and cut some time from that next topic? If there are too many of them, because I expect that there will be.
I think we should try and do 10 minutes. We can have a session after this. I'm going to try and make it as short as possible. So
Okay.
we all need a bit of a break.
Right. So.
Hi, I'm Giulio Pronti, University of Bologna. I have a couple of questions about co-crystals. Say you have a co-crystal with two molecules and you know the way they're going to interact. So you can, in a way, fix the distance and restrain them.
Yes.
I'm telling about this, I'm talking about this because last year I talked with Mary Jane Tremaine, I think. Yeah. And she told me she had tried with a genetic algorithm, and basically she got better results without restraining the two molecules rather than restraining them. So my questions are two. Have you ever tried it, and have you ever tried it systematically?
Okay, the answer to the first one is yes, we have tried it. The answer to the systematic is no, we haven't tried it. My comment would be, and going back to the carbamazepine, and Bill would be able to answer this better than I could about the way that we tackled it with the Z prime of 4, that we anticipated that there would be this standardized back-to-back bonding between the amides. Yeah. And we happened to code it in wrongly, and we never solved it as a result. I think that's correct, Bill. And the simpler approach of just saying, actually, we'll let the global optimizer sort it out, turned out to be the correct way of doing it. But in the co-crystal, some of the data that I showed earlier on was in fact in the case of a co-crystal between two molecules, one of which had a carboxyl and one of which had an amide. And so we anticipated what the ring motif, the R228 motif would be, but we did not incorporate it as a prior constraint, because in our general experience, if Z prime is say 2, and there's not a tremendous amount of flexibility in the individual molecules, it's actually much easier simply to read the two molecules in independently and let them go to where the data says they want to go, rather than trying to anticipate. But if you want to anticipate with the aid of the database, you should be able to construct some molecules that, you know, set the limits between the interacting functional groups pretty accurately. What you may not be able to do so easily, and it's true of that interacting one that I've just talked about, is necessarily predict. You may be able to restrain the distance, you may not be able to restrain the planes, the way in which they interact. Does that...
Wait a moment.
We're talking about later.
Okay, yes.
So, it's your turn now.
Hi, it's Paul Smart here from the University of Sheffield. And my question is regarding Mogul and Isostar as well, with the intermolecular interactions.
Yep.
If you're going to use Mogul to check the geometry of your molecule when you have a solution, why not incorporate that information into the solution process? So as you're optimizing against your powder pattern, you're also, I guess, optimizing against the geometries of
That's a very good point, but to some extent that was what I was trying to convey, except not during the solution process. I would advocate using Mogul at the beginning of the process rather than the end. So, and this comes down to, again, personal experience of just the way in which you, for example, set up a rigid body refinement within Topaz. Life becomes so much easier if you sort out any errant geometry within your molecule at the beginning, and then carry that right through to the final refinement. But if what you're saying is effectively, could you in fact use the information to guide it, then that's certainly possible. Technically, it would mean interacting with the derived database that Mogul has, so it's not something that we've done other than in outline. Bill's shaking his head. I'm not quite sure what he means. But we'll talk about that with Paul, actually. Yep, sure.
Yeah,
Go ahead.
your turn.
Henrik from Stockholm. Have you actually made any further progress in the ibuprofen case? Have you made any further progress in this ibuprofen case, the one you talked about?
In the ibuprofen, I had a trip to Diamond a few weeks ago and recollected the data along with the student Mark, but we haven't sat down, and with the preparation for Hereditary, we haven't actually physically had time to sit down and look at it. But I have good friends and collaborators who have looked at it, and yeah, so we're pursuing it actively. We want to get to the bottom of it, because I mean, I shouldn't trash that solution, because it's basically our solution as well, and it is almost there. There's just something not right about it. I suspect it's disordered in some shape or form. We just haven't figured out what yet. If you've got any great ideas, I'm always open to.
Yes, the fourth one. Yeah.
Ivan Halas from the Zagreb
Could you kindly speak up?
My name is Ivan Halas from University of Zagreb. First, a comment for the incorporation of information from Mogul for structure solution. I don't see it would make much sense, because whether carbon-carbon distance is 1.55 or 1.55 will be insignificant for getting a rough model.
Yes, sir.
And the question is it's related actually to your talk from this morning. In what way does a structure model benefit from, in a refinement, benefit from data collected from variable counting time data?
In terms of the refinement, so the question was in what way does the refinement benefit from variable count time data? The main benefit is the fact that you have higher confidence, you have much smaller ESDs on your reflection intensities at high angle, and so when it comes into the Rietveld, there is less, if you like, slack in the system. When you're fitting a calculated structure factor versus an observed intensity, if you have a high ESD as you would with a fixed count time, then you can have more movement within the structure that satisfies the observation to within an error. If you bring those errors down by using a variable count time scheme, you're effectively constraining the molecular structure to be more precise, more accurate, I should say.
Yuri, wait a moment, one man behind you. Me? Yes, that's you.
Thank you. My name is Ivan. I'm from Russia. How often?
Russia is too big.
Yes,
Would you
from
mind specifying the
from
city?
Dubna, from Joint Institute of Nuclear Research. How often do you use neutrons for structure solution, and do you use
Sorry,
it?
can you start again? I couldn't quite.
How often do you use neutrons for structure solution?
How often do
you use it?
So how often do I use what for?
Neutrons. Neutrons.
Neutrons?
Yeah.
Me personally, not much recently, which is shameful considering I worked at ISIS for 15 years. But I don't want to steal the thunder from the people from ISIS who are going to be talking. The main reason I didn't use neutrons for structure solution was the hydrogenous background problem. We have used it actively in structure refinement, but I would say that the instrumentation has moved on fantastically, and Laurent will give an excellent talk showing just exactly how developments such as Target Station 2 and diffractometers such as WISH may well change that. But of course we shouldn't neglect existing instruments such as HRPD at ISIS, which are very good, provided that you could deuterate your sample.
Yes, but resolution is lower, and maybe it's bad for you to
deuterate, to use neutrons. In terms of the rate, yes, that's certainly true. Yes. So.
Yes, Yuri. Wait a moment.
Yuri Andreev, University of St. Andrews. Great talk, Ken. I just have a very brief comment. You were advocating estimating the ratio of the unit cell to the volume of the molecule.
Yes.
And what I found also pretty useful is measuring the density of the sample, which you can measure pretty accurately these days.
Yes.
And even sometimes you can figure out if there are any atoms in special positions.
It's a very good point.
Yes, that was actually a comment on the question, so, sir?
My name is Mohammed, second year university, Japan. Actually, my question about the overlapping peaks. What is the optimum conditions which can help me to remove this phenomenon about the pattern of organic materials?
So, sorry, say again, in terms of the overlapping...
My question about overlapping peaks in powder diffraction obtained from organic materials. This effect cause troubles in refinement and indexing. So what's your advice in experimental conditions which I can use to reduce this effect?
So there's very little that you can do about the overlap problem other than employ, for example, the sort of things that Lynn outlined earlier. So, for example, texture or differential thermal expansion. But the most obvious thing to do, and this comes with a big condition on it, is to try and recrystallize your sample to see if you can sharpen it up. Because the sharper the intrinsic line width, the less problem you will have with overlap. And we have used that several times, in fact, provided, of course, it doesn't change the crystalline form. Very often a simple, quick recrystallization can result in a peak going from this sort of width to this sort of width, particularly if you're given a sample, say from a pharmaceutical company, where it has been milled and it's intrinsically very broad. You could recrystallize, not change the physical form, and see a massive improvement in the extent of overlap.
Okay, thank you.
Wait a moment, yours. You, precisely.
My name is Sanjit Ghosh from Brookhaven National Lab, New York, USA. So I have a suggestion or comments, or it's not a question. Few weeks ago,
if it is going to be a comment, please be short, right?
So about the radiation damage you have been talking about all through both of your talks, and have you looked into the high energy X-ray? I know in single crystal people have been using in ID15 at ESRF. On single crystal they have used 60 keV or 80 keV X-rays, and they found a dramatic effect of radiation damage is low. Really? And powder diffraction, I know the peaks will be squeezed in if that is a problem. And I have no experience on powder diffraction. I am old enough in age, but new in powder diffraction. But do you see any perspective of using high energy X-rays for less radiation damage?
To be honest, I would have to defer to synchrotron experts on that one. It's not something that we have. I think the shortest we've ever gone to, Bill, is about 0.5 angstroms.
No, we went down to 0.3 with Andy on ID31, I think, one time, and we just saw similar things happening.
Right.
Okay.
So I think it is very material dependent.
Yep, that's the main problem. So, you? Crikey.
Habib from Chalmers, Gothenburg, Sweden. I am continuing the same question again. The variable time and the variable sleet, how they compensate or differentiate each other or complement each other?
The variable count and the variable...
Variable count time and variable sleet. I mean...
Excuse me.
Ian,
excuse me. I would prefer if Jan. Sorry. I would prefer if you ask Kenneth a little bit later. I think that the topic were organic structures now.
Yeah.
All right. Jan.
Okay.
Jan, do you wish to continue?
Sorry, I was just going to jump in and help answer that question. But if needs be, Kenneth and I can get together and deal with it later.
Okay.
Thanks.
Questions? Yes?
Talking about the calculation of the volume. Sorry, I'm Lucia Maini from University of Bologna. We were working with the organic molecule but co-crystallized with ionic material, ionic salt, and we saw that there is a little bit difference in what you calculate, and it's like on the basis of the volume, also with the Hofmann volume, we calculate, and actually at the end what we observe in our structure. So have you the same experience? Can you comment on that, or is it like?
Only, I mean, it's difficult to comment on the specific example. I can only comment really on our general experience, that we have had several examples where the 18 angstrom rule has left us with some ambiguity. For example, wondering if we have a hydrate, because the discrepancy in the volume is quite large. And when you do the Hofmann calculation, you find that the agreement is much, much better. So I'm sorry, I can't really comment on the specific. It's just something that we've started doing relatively recently.
Okay.
Alex Ulenka, Regaco, Europe, Berlin, Germany. What do you think with respect to the very soon operation of XFEL in Hamburg? Are you, as a community, prepared as theoretical methods to explain experiments from XFEL?
So I couldn't make.
With respect to the very soon operation of XFEL in Hamburg, X-ray free electron laser.
Yeah.
Do you think are you prepared from theoretical point of view for data evaluation from from XFEL?
I don't have a clue. To be perfect, I know nothing about XFELs. Better to be honest about it.
Do you mean the resolution on the time scale, preferably?
Yeah. It's femtoseconds and...
Yeah, femtosecond diffraction of femtosecond chemistry, if you wish. That's the topic?
Yeah.
No experience. Couldn't comment.
Okay.
Sorry. It's better that I say that than waffle.
Yeah.
Well, more questions? Yes.
Saul Lapidus from Stony in terms of, you were talking a little bit about eternal variables, when you have things like crown ethers where all the torsions in some regard are coupled because they have to form a ring.
Sure.
Do you know any tricks of modeling that sufficiently to deal with all the coupling?
Do you mean during or before the structure?
You know, before you pull it up, you can just look in the database, but they're going to vary quite a bit from that. During the structure solution part, let's say a simulated annealing run, they're going to vary, but they're going to be coupled in some complicated manner.
Yes. We have actually done, and it was a fair number of years ago in collaboration with some people at CCDC, some examples where effectively you snip the ring and then put an elastic tether at the end of it and use it as soft constraint, so that as the torsion angles vary, the end-to-end distance of the two atoms that close the ring is allowed to flex within a certain limit. And that can help a little bit. But no, in general, what we tend to do with rings is just snip them and let them go fully flexible. And again, just let the diffraction data drive where they're going.
Okay. Are you satisfied with this answer? No?
Yeah? Happy?
Okay.
Yeah.
All right. I was thinking it over. So, any more questions? Yes. It's the second lady. Ladies are curious, I was told.
Hi, I'm Dubravka Shishak from ETH Zurich, and I have a question again considering rings and confirmations. So this Corina software, does it deal with energy optimization or database search considering ring optimization?
It's, I believe, primarily derived from database observations that it uses to calculate what the likely ring conformations are.
Oh, okay, so just if I could make a small additional question. For the softwares which are doing, for the methods which are doing energy optimization, how healthy is it to apply to big rings or for systems which comprise more than one ring in the asymmetric unit? Because from my small experience working with these kind of systems, it does not really work. Yeah, because the differences in energy are so small, and so this cannot support it, and then later data cannot support the differences.
Yeah, I would agree, again, from rather limited experience, particularly dealing with ring systems, but also from looking at programs which will do conformational searching to produce likely conformations. The problem, as ever, is that the energy window associated with a plethora of conformations is very small. So while superficially it looks quite attractive, you think you can narrow down the possibilities with a realistic energy window based on, for example, the difference between two polymorphs of a material. You find that the number of trial structures that you get to evaluate is simply too high. And we've yet to find an example where there is a real benefit to doing that conformational searching in advance. So our observations mirror your own.
Thank you.
Okay, this was the last but one question. The last is mine.
Oh.
Take it easy. On the slide showing Hofmann volumes.
Yes.
You use the V for volume, but once you have got it with bar and one without a bar.
Ah, yes, yes. The actual, let me, where are we?
Here.
Yep. So yes, that is simply the average, the volume. The tabulated volume in Hofmann's table is represented by that V bar.
And that V?
Which one?
In the line. Average volumes V without bar.
Oh, sorry, my mistake.
Okay.
Sorry. Yes, no difference, same.
So if Bill permits,
I'll give you.
Later on, okay? So, thank you very much.
Thank you.
Thanks for all
And
questions.
thank you for the question.